All right. Well, welcome to another exciting embedded microcontrollers class. We've got an interesting lab coming up. We're going to do an RF lab. How exciting. Um, the star of the show is going to be the NRF24L01, which is a chip you can almost see in this picture. Actually, you really can't see that. What you see here in this picture is a module that you buy commercially, which has a little connector that's called an SMA connector, and this here is a, um, a 2 gigahertz dipole antenna, and then what we have over in here is another little chip, which is a low noise amplifier as well as a power amplifier for transmission. That's not on all the modules, but it happens to be on this one. And then this little chip over in here is the heart of the module called the NRF24L01. And these come in a wide variety of flavors. I should have some more pictures so that you can see. Let's see if we can find some nice pictures, actually. NRF24L01. Okay, nice picture in there. There it is. So you can get them in the surface mount flavor. I have a couple of these. You can get them with the pins sticking out. That's actually the one that I find very convenient because you can pull those out and replace them with these, which have the little SMA connector on them. If you use these guys here, you get about a football field transmission distance, assuming it's free air and there's nobody standing in the way. If you use those guys over here with the little antenna, you can go about 1 kilometer. And if you put in a Yagi antenna, one guy was going 32 kilometers in free air, and 16 kilometers with the right style antenna, provided you had everything with line of sight. So you can kind of see the simplified version doesn't have half the chips that this has because it doesn't have the power amplifier. I don't know why Amazon decided to charge $5.20 for it, whereas here it's 25 cents from AliExpress. But you get an idea of the range of prices. These things are basically very inexpensive. And so, I don't know, we'll click on this eBay link for no particular reason. So there it is. I mean, that's the NRF24L01. In fact, I should probably get an image off of eBay. Here is the bottom side of it. And this here, that little squiggly line, that's what they call a microstrip antenna. And then that's a 16 megahertz crystal. You can envision cost reducing this if you already had a 16 megahertz crystal running your Arduino, which we have. And in fact, we have found that there are a wide variety of Arduino variants that have only one of these crystals and one of the NRF24L01s, and then it's all integrated onto the same little board. One is called the RF Micro, which is pretty cheap actually, and comes with everything integrated. So that's kind of nice. We'll have a fun time with this little module on Wednesday. And if I wanted to select 20 pieces, how much would that cost? $14 for 20 pieces? That sounds cheap. I like that. So, but it doesn't get here until the 21st. So there. Well, we have ours now. And what we'll do is we'll provide you with a custom shield, which lets you plug this in so you won't have to do any of the DuPont wiring, because we find the DuPont wiring is a fruitful source of bugs, especially when it's done in a lab. So we'll put another little picture in here, I guess. Oh, cut and paste doesn't work. Good thing. I was worried. Cut and paste would work. Let's see. Copy. Right. And you know what I'll do? So I'll just, for good measure, I'll just take a picture. There. That'll work. And then what we'll do is we'll just slap it in there and make a little picture out of it, just for show and tell. So you can see the two basic variants of the NRF24L01 modules. These are the typical ones that I've been playing with. And this one here is great fun because you can hook it up to a vector analyzer, which is going to give you the power spectral density of the RF output in real time. And you can see exactly what they're pumping out. And that's just because it has a connector which is compatible with the test equipment. So yeah, great fun. Very good for point-to-point communications. But in fact, you can use it to make a little network. And if you don't mind going at shorter ranges, you can get 2 megabits per second out of it. There's a plus version, and then there's the non-plus version. The one without the plus, you can't do the low speed. They don't even have the 250 kilobits per second on the one without the plus. And in certain integrated systems, such as the RF micro, you'll find you're dealing with a chip that doesn't have the plus, and therefore the 250 kilobits per second will not work. That's because the chip isn't capable. So that's a kind of an interesting thing. You ever want to read about these things, what you do is you Google it, and you can find whole bunches of data sheets. So this here is a 75-page data sheet just on the chip. And I think you can, yeah, you can see the block diagram. You can see all the programming information you need, flow charts, everything. It's all in there. Real engineers read data sheets. And there's even a PCB layout example. So let's see what that looks like. Yeah, it looks just like the thing that you buy. So this is the canonical example that they've done. And they even give you the printed circuit board layout, which, by the way, is not breadboard friendly, right? You can't just plug this into a breadboard because that will short out to there. And this will be like ground, and that'll be like 5 volts, and you don't want that because that's a dead short. So, yeah, you got to use DuPont cables when you wire these things up, or the shield that we created for you. In case you're wondering, it's 25.4 millimeters to the inch. So this is not to scale. Let's see. What else can we see about this? Product specs. That's it. So let's get back to the lecture. So that's kind of an interesting thing. Let's see if we can make this full screen. So we've got a little bit of a problem. It works with packets of 32 bytes maximum. So if you want to send a long message, you got to break it up into chunks. And if you want an acknowledgement back, you can either try and do it with a hardware acknowledgement in the data link layer, or you can do it in your application. You could do it in the application layer and cut out all the middleman stuff. Send out a bunch of packets and then ask how many packets were received, make sure it's the same. If it's not the same, figure out which packets got missed and retransmit. So here's the block diagram of the chip. And there's like a lot of technology here in this little chip. LNA stands for low noise amplifier. So you could see that right over here. And that goes up to this little antenna. This is a receive filter. That's a transmit filter. This is Gaussian frequency shift keying, which is a lecture in and of itself. What's frequency shift keying? Do people know about that stuff? Anybody here have a communication systems course?
Could you teach us that or tell us what it is?
Sure. So in the world of modulation, there's a couple of basic terms. I'll say there's 2 kinds of modulation in the analog world: baseband modulation and broadband modulation. In baseband modulation, what you do is you take a signal like 0 and you assert a voltage like ground. And you take a signal like 1 and you assert another voltage like 5 volts. That's baseband modulation. If you have more amplitude, you cause more deflection. from whatever energy you're using. So if your energy is coming from the pressure wave of sound and it impinges upon a microphone, you can use that to deflect a needle that carves out a groove in a record. So if you actually have a physical LP turning and you take your fingernail and you touch it to the grooves, you can actually hear the sound coming out because it's baseband modulated onto the plastic, or I should say the vinyl of the record. So that is a baseband modulation. It's very common modulation. If you think about it, um, it's probably the oldest of modulation techniques. For example, if you're trying to communicate with talking drums, right? Talking drums are hit and they're somehow able to send a message through the air because of their very low frequency. They can penetrate the jungle, so-called jungle drums. If you have a POWs tapping on pipes so they can communicate with Morse code, that is a form of baseband modulation. Now, if you then said, well, look, what I'm going to do is I'm going to try and get this to carry over long distances. Like, let's say I want a transatlantic telegraph. That's something that Samuel Morse was kind of interested in doing. So what do? Well, we and Marconi made a business out of this. You take a carrier, which might be an AM carrier, normally amplitude modulated carrier, but you just send it out as a single tone, and then you interrupt it, and then you send it out again. That is a form of broadband modulation, because what you need to do is you need to decode that carrier, and the carrier is going to be an RF, that is a radio frequency that is going to be well into the hundreds of kilohertz, if not higher. And that's called continuous wave modulation. It's a form of broadband modulation, just like baseband modulation, but with a difference. And the difference is you're working at a much higher frequency, in a radio frequency. Then along comes this idea that you want to transmit voice. So instead of taking the carrier and interrupting it in order to create a dot and a dash, just like you would do if you were going to create two different tones, one for dot and one for dash, what you do is you modulate the amplitude of the carrier in order to be able to transmit the voice information. So the voice information will happen at a far lower frequency, but you'll bump it up to the high RF frequency by virtue of what's known as a balanced modulator or ring modulator. And so what that does is it multiplies the incoming signal against the carrier and gives you two what's known as subbands. Probably need, can I actually write this stuff down? Just a minute here. Shift, let's do a little, we need this actually. Let's do what do we call this? Communication systems. And this is the Father Guarducci School of Education. So this is everything you would have forgotten 4 years after you graduated. We're going to teach it to you in about 10 minutes. And this is assuming you had a communication systems course and you went 4 years without using it. This is all you'll remember. There's two kinds of modulations. There's the baseband, and then there's the broadband. Okay. With baseband modulation, we use the information, let's see, use the signal, well, information, use signal directly. So we'll have jungle drums. What's another one? How about smoke signals? I like that. Smoke signals. Ethernet, that's a good one. Ethernet is a form of baseband modulation. Ones and zeros. Zero is equal to ground. 1 is equal to 5 volts. That's baseband modulation. Another example is vinyl records. I think I spelled vinyl wrong. No, it's not venal. I think there's a VI. Vinyl. Did I spell it right this time? I guess that's vinyl. So then for broadband, we have other forms of modulation. We have amplitude modulation, AM, and that's where we have the signal multiplied by the carrier, which gives us two subbands, which is equal to the signal times the carrier is going to be signal plus carrier and signal minus carrier. So if you have a signal that's, let's say, a kilohertz, and you multiply it by a carrier that's, let's say, 2 kilohertz, then I would have the signal plus the carrier, that's 3 kilohertz, and the signal minus the carrier, which is equal to 1 kilohertz. But presumably you could use carriers in the megahertz or gigahertz or whatever you like. Then there's another kind of modulation called FM. And what this does is it phase modulates, or frequency modulates, it's better. Frequency modulates. That is, modulates means to change the carrier to reflect the amplitude of the message signal. So if I wanted something linear, I might say, okay, if I go up to 1 volt, I will frequency modulate up to the limit of the band of my FM transmission. So for example, 91.5 megahertz can be equal to the carrier, but when the signal comes in at a very strong, let's say 10 kilohertz, I might modulate this carrier up to a frequency of 91.55 megahertz, right? So I might have a 50 kilohertz deviation. So the frequency of deviation, this is typical FM stuff, might be 50 kilohertz. So then your decoder has to go and detect the deviation of the carrier in order to be able to reconstruct the original signal. And this doesn't even get into what you do in order to be able to sample stereo, which requires a 38 kilohertz resampling of the transmission signal because it goes from the left and the right and uses a pilot tone at 19 kilohertz. So this is a sort of a broad idea. So now these are all what I would call analog. This is all analog broadband communication. And I wrote analogy, but I should have written analog. Or maybe the spell checker did it. I'll blame the spell checker and the communication. This is not working. There, communication. So important. So now we want to get into the next phase of communication, which I shall call digital broadband communications. Summary. And so that's where we're going now. This is our next stop on the way to the NRF24L01. So in broadband digital communications, what you want to do is you want to obtain a, I'll say, a phase amplitude constellation. Phase amplitude needs a dash. Constellation. So what we'll have is different symbols, perhaps in a 16 by 16 matrix, each with a different phase and amplitude. So this is known as PAM, for phase amplitude modulation. And what you do is take the log to the base 2 of the number of different symbols, which I will call n, is equal to the number of different symbols, and assuming all symbols are equiprobable, you have the number of bits. You have the number of bits encoded per symbol. Okay, what does that mean? So if I have a 16 by 16 matrix, I have 256 symbols. If I take the log to the base 2 of n, I get a number, which is like 8, because 2 to the 8 is equal to 256. Right? So here's the example. If you have a PAM constellation of 16 by 16 equiprobable symbols, then you have n equals 256, and 2 to the 8 is equal to 256. Therefore, the log to the base 2 of 256 must be 8. And so we can compute the number of bits per pixel as 8 bits per I'm sorry, not pixel, but symbol. This gives us 8 bits per symbol. So now all we need to do is create a receiver that can detect the various phase and amplitude signals as they come through. And a phase amplitude signal is going to be a sine wave that's been shifted by so many degrees and given an amplitude at a certain, at a certain intensity. And so now what we can do by detecting that, perhaps using filters, is we can proceed to determine which symbol was transmitted, and that will give us an 8-bit byte out of each one of the symbols. And in fact, you can make the constellation as large as you like, as long as you can transmit it reliably when faced with so-called channel noise. Gaussian, let's see, we'll do the next one now. Frequency shift keying, also known as shift keying, uses frequency modulation to transmit your symbols. And so what you can do is you can shift to a wide variety of different frequencies. And as your next frequency comes in, you're going to get a different symbol. And the same thing applies in terms of this is known as the Shannon limit theorem, right? So this is the Shannon limit, says that the amount of information measured in bits is equal to the log to the base 2 of the number of symbols, assuming each symbol is equiprobable. And you can make that happen, right? You use a code book for that, and you do what's known as channel coding before you transmit your data. So that's frequency shift keying, and you can see this being used even in the audio world. So, for example, the Kansas City Standard is good for cassette recorders. Actually, it's a lousy standard. I used to use it. And it runs at 1200 hertz. There's only two frequencies and 2400 hertz. And that's a bad standard because they are harmonics of one another, and it confuses, when you have bad tape, it confuses the decode circuitry. They used to use it on introductory computers like the PET and the Kim 1 microcomputer, Kansas City standard. Haven't thought about that in a long time. That is an example of frequency shift keying, and you can see a definition of that, I should think, Kansas City Standard Wiki. And yeah, audio cassettes. Swiptic, Southwest Technical Products Corporation, $80 in 1976. That's when a buck was a buck. And look, you could get 2,400 bits per second. Wow. But I'll tell you, that beats having to type it in. Kansas City Standard. And so that's a capable of storing directly onto an audio cassette because it's using audio frequencies. In fact, we could probably use our Arduinos both to synthesize and detect my old Kansas City Standard tapes, which, by the way, I kept because I'm an absolute hoarder and I know it's a sickness, but I don't care. And so you can use this to effectively store your programs. And I remember getting my programs on little floppy records like this, and you could play them on your turntable if you had such a thing, and then you could decode them with your magazine, and your computer programs were there on the records. Isn't that cool? And you could print these very inexpensively, and it beats having to type in the little microcode that's underneath, because you have to type that in by hand. If you make a mistake, it doesn't work, like, at all. So that's a kind of a cool thing. The other place you want to go, yeah, here's the computer I started with, the Kim 1, that used it. You could go at 1200 baud with hypertape. I used to do that, actually. So there's another standard that you can use two frequencies for, and you use it all the time. You use it all the time. You're going to love this. See if we'll do another one. Right, we kind of digressed into this digital data communication systems discussion, but I think it's important. So in this standard, we use DTMF. That stands for, does anybody know what that stands for? Never heard of that? That is the dual tone multiple frequency standard. Where do I find that? Anybody know? Nobody knows? Oh, you're going to love this. All the touch tone phones. So DTMF, that's a well understood standard, and they were smart about it. They didn't use harmonics like they did in the Kansas City standard. Instead, they used non-harmonic frequencies, and they play them together at the same time. And there it is. DTMF. There's the touch tone pads, and when you hit these things, they make these tones, which you could record this onto cassette, and if each one of the keys are equiprobable, then you actually do have a 4x4 matrix, which means 16 different symbols. So I could take essentially log to the base 2 of 16 and get a number, which would be like 5, I guess. Right, because, well, is it 4? 2 to the 4 is 2 times 2 is 4 times 2 is 8 times 2. Yeah, 2 to the 4, sorry. So that would be like 4 bits per symbol if I use these numbers, and each one was equiprobable, and I could encode my digital data in that way. Dual tone, multiple frequency. And in fact, the standards are such that you can actually see what those frequencies are. And that's pretty cool, because what that means to me, the Arduino programmer is I can generate these frequencies by creating sine waves and adding them together and then just outputting them onto my Arduino, and I can start to dial the phone with the Arduino, right? How cool is that? In fact, if we go to my little dial program, when you look at the preferences and you look at the dial setup, one of my options is to dial with the speaker using the Java program. But doing it with Java is not as cool as doing it with the Arduino, right? Because we're Arduino programmers now. So it's probably the case that we could sit down and have the Arduinos do our dialing for us instead of our old modems. So that's pretty cool, actually. And you could see these are definitely not harmonics of one another. So it's pretty cool design, actually. And then there's I guess it makes sense to sort of take a picture or something, right? Let's do that. Take a picture and throw it in there. DTMF. There. And people know exactly what you're talking about. And you could take apart these phones and get this keypad right out of there, especially if you've got an old phone hanging around like I do. But I actually use my phones, so don't do that. So here's the Gaussian frequency shift modulator. And so now we have an idea about how we can encode binary data. And then you need, of course, if you're going to receive a demodulator, transmit filters. I don't have to get into filter discussions because that's going to take a while. There's this RF synthesizer. Now, what he's doing there is he's doing a multiplication by the carrier that's coming in order to give you the positive subband and the negative subband. And so this is a decoder right there, demodulating. He can filter out one of the subbands, and then he has to go through his little GFSK demodulator. And what that is a big filter bank. And it just says yes when it sees the various symbols coming through, which are coming through at different frequencies. And so if he builds a filter bank that's tuned to each frequency, he can just tell you what symbol it is as it comes in. So that's pretty cool. Let's see now. What else do we need? SPI. We know what that is, right? Because we've been playing around with SPI. So these things have SPI interfaces, and the SPI interfaces are going to give us a high-speed bus with MOSI, MISO, serial clock, and a chip select, and an enable. You can use the enable to turn it off. Let's see. So he's got a little bus in here, some FIFOs. That's first in, first out transmitters. So when data comes in, the FIFOs will store the data and then shift it out as it gets ready to transmit, because it can come in faster than it can transmit. And when the data comes in faster than it can gain access to the SPI bus, then it'll store it in the FIFO. So he has limited storage in here as well. This is a lot of chip, really. A couple of things about this. It's a 5-volt tolerant for its signals, but when you go to power it, you really have to wire it to 3.3 volts. If you try and wire it to 5 volts for power, you burn it out. I'm not quite sure how fast. Milliseconds? Nanoseconds? Fast. Faster than a blink of an eye. Fast. This is the pinout on the chip. And I show you this only because it's a complicated chip to have to wire. But basically, the only thing we end up having to wire is the SPI bus, which is chip enable, chip select, serial clock, MOSI, MISO. Interrupt request is often left unhooked, and power and ground. Presumably, you won't need to do that for this lab because we'll have the whole thing set up on a shield. And then there's a bit of a finite state machine that this thing is going to, let's get rid of the ancillary PowerPoint flotsam clogging my desktop and see if I can make this just a wee bit larger. There we go. So what'll happen is you'll power on the thing, he does a reset, and then he's got to go through a startup sequence, and then he goes in and he does a standby. once he gets into standby mode, he can go through a sequence where he does a transmit and then goes back, or he goes through and he does a receive, and then he goes through receive mode, and then he can go back to standby. So he's got transmit mode, standby, receive mode, standby. And you got to do it in separate. You can't transmit and receive at exactly the same time because you're going to swamp the antenna. Your low noise amplifier will be set up to receive only after you're done transmitting. So that's the NRF24L01. Here's the FIFO SPI module comes in. It's got a whole bunch of control stuff that it can do, and then he can generate acknowledgments. He can transmit stuff, hold on to a number of payloads, and the payloads are all 32 bits. So you got to chunk everything into 32-bit quantities. Here's an application. You can do a mesh. Isn't that cool? So what we get when you use these things is you get a library, and I'll show you how to set that up. And then what you do is you'll get our code, and I'll set up to transmit, and you guys will set up to receive. I don't think we're going to do a mesh network in the lab because, I don't know, that's too complicated by half. But what's nice to know is that even if you have a relatively short range, if you have a number of nodes spread out throughout a sensor mesh, you'll be able to use those to store and forward over a longer and longer period of range. And it adds a lot of value to the network to know that you can get to any one node from any other node. But there are certain nodes that'll be critical, like this one, which is X'd out, which would keep you from having access to the others. So if one of these nodes goes down, it could take down a whole branch of your network. And so it allows you to do what we're going to do in the lab, which is data link layer peer-to-peer transmissions. And there may be an opportunity for us to be able to test reliability. And in principle, if we have to do a lot of retransmits in our environment, we'll find out the hard way, I should think. So that's my bird's eye lowdown on communication systems. The communication systems topic is actually a 15-week course. And they probably don't tell you about jungle drums. I may be the only one who actually tells you about smoke signals and jungle drums, but they're out there and they actually work. I think West Nigeria has a tradition of trying to carry on the talking tongue drums and that sort of thing. It's kind of interesting. And it's one of the West Nigerian princes, Baba Olatunde, continues to do shows. I think he's still around. I don't know if he's still alive, actually, but I think he might be. And he was doing this sort of West Nigerian talking drum music. It's kind of interesting stuff if you like multicultural experiences. So bottom line, you need to be able to code these things. And therein lies the rub. So I have a transmitter and a receiver. And this one is receiving and showing text, which is empty. And this one is sending, which is showing text, which is not empty. And I also have a structure. This is a little bit more C code than you might have seen in the past. But when you look at it, you'll see the structure is basically just like a class with a difference. And the difference is it doesn't have any methods. It just has data structures in it. So this is a primitive data type, the int. The float's a primitive data type. The char is an array of text, which has been set to text to be transmitted. And then the package itself is a structure which you can create an instance of. So you use lowercase package for the structure, and then you give it the variable name package or Here's another one called data. And so what I end up doing here is I have my own serial port, which I can transmit. I can show what I'm transmitting and what I'm receiving on. I do a radio.begin. So that in and of itself requires you have a library. So there's the RF24.H library being included. And what you can do to make sure you have it is if you go to your sketch and do include library, you can hit manage libraries. What I'll do is I'll show you what's been installed. And then I'll put in RF24. And so you can see there's an NRF Lite library, which is what I've been using. And then there's another library in here, the RF24. You can use that too. And it says I need to update, but I'm not gonna, because I think I downloaded this from GitHub, which may make it work properly. Whereas if you get it directly from here, I'm not sure it works properly. We can look at that more when we get into the lab. And so then I've got my little transmitter. I've got my receiver. Now the receiver has knowledge about the structure that I'm going to transmit. It doesn't know what's in the structure, right? Because his text is empty, his temperature is 0. But we want to be able to transmit something that will fill the structure and then allow him to print it. So what he'll do is he'll set his power level to minimum. And this will only work if you have the actual modules with the NRF24L01 plus in them, because otherwise minimum powers don't, so minimum speeds don't work. Minimum powers will work, I think. And also need to have a channel. There's a bunch of different channels that you can use. And these are constrained areas within the frequency range from, I think it's like 2.4 gigahertz to 2.5 gigahertz. So there are small little chunks in that broad band of transmission. And you want to make sure you're communicating at the same channel. We'll all communicate on the same channel when we do our lab. You'll be able to hear everything that gets transmitted. And so then here's my little setup where I set up the level, the data rate, a little pipe just coming in on channel 115. Delay for a second for a setup. Complete. And then let's see. I write this data along with the number of bytes in the data, and that's what size of is doing. So if we look at the data, that is of instance package type. And then, let's see, I print out the data ID, put in a new line, my present temperature and text, increment my data ID, increment the temperature for no particular reason, just so it will change, and then continue. So let's see if we can make this work. So this is going to the monitor called 11420. It says it's done uploading. So if we take a look at that monitor and go to 115200, there it is. Setting up, and now he's transmitting. So that's cool. There it is, transmitting away. Now, there's nothing receiving it, so you can tell it doesn't know that nobody's receiving it. It's completely open loop transmission, completely unreliable. Obviously, there's no receiver. So this is just transmitting out into the ether for the space aliens to hear it. And what are those space aliens thinking about anyway? So now I've got to upload the receiver to the other Arduino. So I need 2 Arduinos for this project. So first thing I'll do is go to my port and pick, the other Arduino, 11440, And let's open up the receiver there. (11440). And then let's take a look at what they have to say at the receiving end, and that has to be 115.200 as well. And it's receiving stuff, which is cool. And so what we want to do is we want to see the transmitter and the receiver at the same time, but there's only one monitor and only one Arduino running. So what we'll do is we'll go to a separate terminal. I'll call it Cool Term, and we'll go into the options area and make sure we're running at 115.200, and then pick a Arduino to listen to, hit OK, and then connect. And that'll be our transmitter. And so we'll have the transmitter, and then we'll have the receiver. Isn't that cool? So now we can see both at the same time, transmitter and receiver. That's like a demo. What do you think of that? It's a demo. Doesn't that look like a demo? A demo that actually works. Huh? 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 And you can see the numbers are incrementing on the transmitter side, and they're also incrementing on the receiver side. So what happens if I disconnect my, let's change it. Change it up. Let's change the thing we're going to transmit so that it reads something like Mickey Mouse is my hero. And then what we'll do is we'll take note of the fact that we're connected to 11420. Disconnect right now. We'll connect this up to 11420. So we'll choose a new port, 11420. All right. Upload it. Then go back to choose the other port. Bring up our serial monitor. And connect. Now the transmitter's reconnecting. Mickey Mouse is my hero, and it comes out at the other side as well. So there it is. We have essentially shown transmission and reception are occurring. So there you have it. And it doesn't say Mickey, it says Mick Mouse. Oh, there's a typo. I have to recompile. Oh, no. So there it is. My little demo of the NRF24L01. And that's my plan for this Wednesday. So we're each going to get one of these, and we're going to be able to do RF transmissions. And this is, the ISM, or instrumentation and medical band. So you can use this in a license-free fashion globally. There might be some interference with various microwave ovens and such. That's part of the reasons why you can use it without a license. 2.4 gigahertz is essentially an unlicensed band. It's nice and fast, and you can run your own transceivers. And one nice thing here is you can see sort of like how many packages were transmitted versus how many were received. You can see if things were being lost. So that's cool. I like that. So let's disconnect this, and we'll close that. We won't save it because we don't care about it. And then we'll close this out. And so, hey, what'd you think of that one? Right? Let's take a look at the code. This is as small as I could possibly make it. So I got the receiver on the left. I got the transmitter on the right. The print statements are coming out right in through here. The only time when there's any transmissions going on is when you do a myradio.write. And that takes the data structure and sends it out, hopefully with no more than 32 bytes in the transmission. Any questions about this? That's fun, isn't it? Very fun. Very fun.
Great. I'm actually excited for the lab.
Yeah, isn't that exciting? So we're going to do a real digital data transmission thing. And you can do the mesh later. There is interesting mesh software. I've been looking at it. I've never tried it myself. I think it's something we should try and do at some point, but I'm a little bit worried about um, the number of new COVID cases. And I'm thinking if I have to go online and do remote learning with this lab, we're going to miss out because we're going to miss out on the fancy hardware that I have planned.
How many more labs do we have left?
Well, that's a good question.
I know we did 11 last week.
Two. I guess we meet on the 25th. I'm not sure about that.
I mean, I know for like probably we could do this week's lab for sure, and then the next week's lab is going to be. I mean, if it's online. Um,
Well, I mean, before Thanksgiving is the 26th.
right.
The 11th and the 18th are well in advance of the Thanksgiving
Hmm.
recess. Thanksgiving recess is the 21st. So what that tells me is that there's only two labs that we have left to do in person.
There's no classes on the 25th, I think. It's Thanksgiving break.
Yeah,
Yeah.
well, we don't come back after Thanksgiving recess. So I don't know if you guys are aware of this, but my understanding is that after the 21st of November, all learning is remote learning. So that doesn't mean the labs stop. It just means we can't meet in person. We have to find other ways in which to do the labs. And that could include things like simulators or writing code or, I mean, other stuff. But it changes my plan. You know, you ask how many labs are left, and I'm thinking what you really mean is how many times can we meet in person? And the answer to that is we meet on the 11th, that's this week. We meet on the 18th, that's next week. And then we are done with our in-person laboratory meetings. So, and that's because after the 18th, there's the 21st, which is a Saturday. That's the beginning of your Thanksgiving recess. And according to my understanding is on the 30th of November, classes resume online only. And so what that means to me is that our next lab will probably be December 2nd. So we'll have a lab. The way, well, we can do this planning now. Here, we'll do it now. The lab that's coming up, and I can sort of show it to you. If I can get my Blackboard thing to run. I think it's number 10.
The one due this week.
Yeah, that's number 10 is due this week. We're going to be doing lab 11. So we'll do lab 11 on the 11th. We'll do lab 12 on the 18th. And then we'll do the Thanksgiving break on the 21st. Classes resume online only on the 30th. So then on December 2nd, we'll have lab 13 online. And we'll have lab 14 online. And those will be, here, I can write this down for you so you can see it. Okay. And so what we'll do is we'll do lab 11 on 11, 11, 20. And we'll have lab 12 on 11, 18, 20. I think that's correct. We're going to have Thanksgiving break. 11, 21, 20. Tea giving break. And then I think we're not back until 12 to 20. That will be lab 13. I guess you should do it this way, right? Lab 13. No. Lab 13. And that'll be online. Right? So now the rest is online. So now lab 14, which is going to be 12, 9, 20, will be lab online. And this will be the last lab. Which is very sad because this is a very good part of the course. I think it's the best part of the course, me personally. So anyways, what we'll do is that's the plan, unless we have to go online sooner. Are there any questions? I think that's how you wrap up the semester, as near as I can figure. That's my understanding. Does that look right to everybody? I've got my calendar in here,
right.
and yes, go ahead.
No, yeah, I think it looks right.
Yeah. So yeah, we wouldn't have a lab. I think somebody said you don't have a lab on the 25th because there's no class because it's Thanksgiving recess, and that's correct. You would not have a lab on the 25th. And so that's the way it looks. So when someone says, how many labs do we have left? 4, with 2 in person and 2 online in theory. In theory. And I'm going to say in theory because I don't know if we're going to have 2 online or if we're going to have 3 online. And this lab here is the NRF24L01 lab. And this lab over in here, I was sort of thinking about doing an Ethernet lab. If we're going to do it in person, we can do an Ethernet lab. If we're not, we can't. So this lab is a question mark. But my plan for this week is to do an NRF24L01 lab. That's my plan. And any questions? Cool. So that'll be fun. We'll have a good time with that. And then what I'm going to do now is save my little PowerPoint presentation because I want to keep these dates handy. And then I wanted to have a little bit of a discussion with you guys about the about libraries, and maybe just a little bit more about C and C++, because it's one of those things where I think sometimes we lose sight of the fact that we're actually doing C programming and C++ programming. So when you see something like this, structs and type defs and such, these things are C constructs. In Java, we don't have type defs. We don't have structs. We do have enums now, but they didn't used to. So, for example, if you wanted to do, I'll do a little real-time example here so you can see what's going on. we'll make a sketch from scratch because that's always useful. All right. This here, this sketch, this is actually a little C program. And what you can do in here is you can define a number like n and set it equal to 20. And then over in here in your loop, you're going to have access to that number. In fact, what you could do is you could put it in the setup. Setup will have access to the number. It's global. And what you can do is do a serial.begin, put it up at, I don't know, 9600 baud, and then serial.println, hello world. In fact, you could probably do serial.print, and you could print out n. And that's a perfectly legitimate program. And you can run the program. Well, you need to give it a thing. How about we'll call it define example. Save. And now what we'll do is we'll take a look at the serial monitor, and it says hello world 20. That's fine. That's just what we'd expect. Now let's assume we would like to create a header file. So what we'll do is over in here, we'll say new tab. We get a little prompt down at the bottom. And what we'll do is we'll call it the define example.h. You can call it whatever you like. And then what we'll do in define example.h is we'll take our little define right over in here, and we'll put it there. Okay. And now what we'll do to gain access to it is we'll say # include, and then quote, define example.h. And now what that'll do is it'll run through not the C compiler, but the C preprocessor, take everything in here and expand it so that it's in here. And so now we'll have access to the header file that's there, which could be held in common with many programs. And now when we run the program, it compiles it, it sees it, and it runs it. Now here's the interesting thing. If you go into the sketch and you want to show the sketch folder, what you find is there's your .h file and here's your INO file. So that's all very cool. In fact, that's kind of what we would have expected. And it makes sense for us to be able to add whatever defines we like to in here and have them included, and perhaps this will increase the compilation time. But wait, there's more, right? What else can you do? Well, if you wanted to, you could define a class. So we know about classes because some of us have taken Java programs, but maybe there's a class called test. And in the test class, we have a, let's see, a public integer called the grade. And it's equal to 100. And so in principle, we could put a little semicolon at the end because I think you need that. And this might compile. And it does. Compiles good. Well, compiles okay. Compiles well. Well, it compiled, put it that way. So now here comes the test, which I will call the final. Oops. And now when I go to print the grade, maybe what we'll do is we'll define n to be 100. And then when we go to create the grade, we'll set it equal to n, so you get 100. And now what we're going to do is we're going to print final dot grade. There. I want to print my grade. And it's contained in the instance of the final class, which has a public instance variable, well, a public, what will we call this? Primitive data type, I guess, called grade, which is of int type. It's set equal to n, and n came from the define example.h. Am I going too fast? Is this all right? People can read this sort of, right? And so let's see if that compiles. It likes it, right? So what are we dealing with here? This is not just a Java compiler. I'm sorry, not just a an Arduino compiler. This is a full-fledged C compiler. It's an IDE that has been integrated in with a C++/C compiler. And if we run this program, what do we get? Nothing. Doesn't work. Broken. Oh, yep, there it goes. So that's a that's a way for us to be able to proceed and do what now? I don't know. Come up with interesting classes that we can then proceed to compile separately, right? So what if you know, for example, that this include is simply going to take everything in here and expand it over there? Why not take this class, cut it from here, and just kind of push it over here? Because that's what includes do. They take everything from here and they push it into there. You can do that, right? That should be okay. And it's done compiling. And you hit run, and what does that buy you? Nothing. Headaches. Doesn't work. Oh, it does work. Okay, so there you go. And oddly enough, it just worked, right? And now you can see how you can build large sets of separately identified classes and get that clutter out of your code, and get it out of your program. And then, if you wanted to, you could go one further. You could define the header for this class, and then proceed to take the class itself and put it into a separate file and call it define example.cpp, or I don't know what you might like to call it. That might be all right, I suppose. New tab. Let's call this define example.cpp. I think we can do that. Now we're getting into the limits of, what seems to work when I use these compilers, because after a fashion, this tends to break. But we'll try it anyway, because what the hey. And I'll show you what breaks and what doesn't break. That's actually educational. So we'll take this class over here, copy it, and we're going to put it over here. And then I think we might get an error. Yeah, he didn't like it. Why? Because we didn't include the define, right? And I can't do the define. Why? Because I would be defining the class twice. So what you need to do is either copy this over or get that class out of there. So let's put that in here. That define with the constant has to be available. And let's see if we can get this compilation to work. Yep, there you go. So that's good. That's very good, actually. And now what we'd like to do is we'd like to be able to have this compile separately and still have a reference to it inside of the define example class. So to do that, what we want to do in this header is come up with a way to tell this program about the data types inside of this program in the header so that it can be compiled separately. And that's about as far as I got with the Arduino IDE before things started to go south on me quickly. You might say I lost patience with it, but thankfully, I think I may have found someone who's going to take up the thread on this and try and solve that problem. Because normally, this is not a hard thing to do in a C++ compiler, but for some reason, I just haven't been able to get the Arduino IDE to cooperate with me. But you got right now to the limits of what it takes in order to create a library. Because once you have your own libraries, what you can do is you can host them. And when you do host them, and this is kind of cool, actually, you can look at this. Go to the preferences, and you can put in your very own web page. And what'll happen in that web page is it'll have a little JSON data structure. JSON is just a stupid data structure programming language for describing things. I don't know how stupid it is. It's about as stupid as XML. So it's stupid. And then what you can do when you have those data structures in your search area is when you go to look for your libraries, when you look to the manage libraries thing, it will show up. And so that's a convenient thing. In other words, all of these libraries came from somewhere. So when you click on more info, that more info field is part of the JSON data structure that people are putting up on the web pages in order to advertise their libraries. So if you're a hardware manufacturer, and I dare say I might actually be a hardware manufacturer because I make hardware. I don't know if that makes me a hardware manufacturer or not. Maybe it just makes me a hardware hacker or something. But anyways, you want to have free libraries for people to use because that is not only free, but open source, free and open source libraries for people to use because that is the Arduino way. They have, if you're going to make some hardware, you open source the hardware, then you give away the software, and somehow the money comes in from like the heavens and gets into your pocket and you can go out to eat or something. I don't know. So, I go and I click on these things, and a lot of times the libraries have been taken down because according to Arduino Central, too many people were hacking these libraries and it just discontinued them. And so they decided that everybody should move to GitHub, but not everybody who contributed a library actually did that. And they made the change like in December of last year. So they basically broke all of the links and all of the open source libraries that everybody was writing and contributing so graciously and generously because, I don't know, security. Because security. Is that like a reason? I guess. I don't know. So apparently people were deploying code that actually did harm. I guess. Anyway, that's a problem. And so they had to try and address it by shutting down the website. And that kind of sucks, really. So we got to find new ways to deploy our our Arduino code. And we'll probably do that by putting them up on our own little website or something like that once we get to the point where we're writing our own libraries. So that's my shtick on libraries and Arduino programming. And now you've had a little example of header files and C++ programs. This is a very trivial example, but I wanted to do a simple first example and just give you guys a little insight into how you can make your code scale a little bit when you want to make your systems larger, because putting everything in setup and loop kind of doesn't make sense. I mean, that's okay for a simple example, I guess, but if you want to do anything real, you want to go a little bit beyond structures, doing this RF radio and having an instance of my radio on pins 9 and 10. That's the way to do it. And so when you go and you look at the sketch folder for the RF radio thing, you'll see there's the sketch, and then here's like the code. But if you were going to do this as a proper example, like you might see over here where we have a channel scanner. Look at the folder on that one, and you'll find there's a bunch of examples, and then there's a bunch of library source code, and here's the C++ and the header files, and then there's this thing called library properties, and you can look at that if you like. There's all this other extra stuff and more, things for you to look at. The libraries can get quite large, and it's kind of an interesting thing when you look at it that way. And this is how people structure their libraries so that they don't have to constantly recompile everything. So I see I've gone over just a little bit. I hope you guys have a nice day, and then thank you for your attentions.
Thank you.
Thank you.
Thank you.